The topic we are going to discuss now is catalysis. Let's find out what is catalysis. See, we need to first understand the term catalyst. Consider this reaction KClO3. When it is heated, it gives a mixture of KCl and oxygen gas. You can balance the equation like this. Fine. So, on heating, KClO3 decomposes to give oxygen gas. If the same reaction is carried out in presence of MnO2, then the reaction takes place in the same manner, but the only difference is the reaction takes place at a faster rate. MnO2 will be recovered as such after the reaction, and the quantity of MnO2 you require to speed up this reaction will be very small. So, here MnO2 is said to be acting as a catalyst. So, let us define catalyst on the basis of this observation. A catalyst is a substance which is used in very small amounts and which speeds up a chemical reaction to which it is added without itself being consumed. Speeds up a chemical reaction without itself being consumed in the reaction. Such a substance is called as catalyst. A substance which is used in very small amounts, which speeds up a chemical reaction without itself being consumed in the reaction. There is no change in the quantity of catalyst at the end of the reaction, and there is no change in the chemical nature of the catalyst in the reaction. Such a substance is called as catalyst, and the phenomenon is called as catalysis. The phenomenon is called as catalysis. Now, there are some more related terms. Inhibitor. This substance decreases rate of reaction. In other words, I can say negative catalyst is called as inhibitor. Catalyst, the term catalyst is always used in the positive sense, a substance which speeds up the reaction. Whereas a substance which slows down a chemical reaction is called as inhibitor. It slows down or decreases the rate of chemical reaction. Such a substance is called as inhibitor. For example, H2O2 decomposes to give H2O and O2. A small amount of urea added to this substance will decrease the rate of reaction. That means urea stabilizes H2O2, or I can put it in this way, urea is an inhibitor for this type of reaction. It's a stabilizer, inhibitor. Negative catalyst decreases decomposition of H2O2. You can as well use sodium stannate, urea or sodium stannate. These substances in this reaction are said to be acting as inhibitors. So, we have got familiar with two terms. One is catalyst, another one is inhibitor. Catalyst speeds up reaction, whereas inhibitor slows down a chemical reaction. MnO2 catalyzes decomposition of potassium chlorate to oxygen, whereas urea or sodium stannate decreases the rate of decomposition of H2O2. Now, there are two more important terms. Let us get familiar with them. One is promoter. Promoter is a chemical substance which enhances activity of catalyst. It increases activity of catalyst. You are familiar with this example. This is very popular. N2 plus 3H2 gives rise to ammonia. This is a very important industrial reaction. Here in this reaction, catalyst used is Fe, and promoter used in this reaction is molybdenum. In presence of molybdenum, the activity of Fe towards catalyzing this reaction will be enhanced greatly. So, promoter is a substance which increases the activity of catalyst. Now, another term, Poison. This is a substance which decreases the activity of catalyst. It decreases the activity of catalyst. Decreases activity of catalyst. Let me give you example of this. AS2O3 poisons platinum in contact process. Arsenic oxides, they act as poison for platinum catalyst, which is used in contact process for the manufacture of sulfuric acid. Another example of poison, example 2, quinoline poisons palladium in Lindlar's catalyst. Quinoline is added intentionally to decrease the activity of palladium. The catalyst mixture is called as Lindlar's catalyst. It is a mixture of palladium, barium sulfate and quinoline. In this mixture, quinoline acts as a poison. It decreases the activity of palladium. The reason is, if you start from alkyne, you end up with alkane in the absence of poison quinoline, whereas in presence of this poison quinoline, you end up with alkene. So it is possible to bring about partial hydrogenation of alkyne to alkene in presence of quinoline. So here poison is added to the catalyst intentionally to bring down the reactivity of catalyst so that you get partially hydrogenated product rather than fully hydrogenated product. So that's about poison. Now let's learn about some important characteristics of catalyst. Characteristics of catalyst. Number 1 is it is used in small amounts. You require them in very small amounts. Next, not consumed in the reaction. So you can reuse catalyst several times. You need not every time add catalyst to the reaction. It can be recycled. It can be recovered at the end of the reaction. It decreases, this is a very, very important point, it decreases activation energy of the reaction. This is how catalyst helps. It lowers the activation energy of reaction. In this way, it can increase the rate of reaction. Look, if you see the energy profile diagram for a chemical reaction, imagine this is the average energy of reactants, this is the average energy of products. This is an exothermic reaction. You can realize reactants have to cross this energy barrier so as to reach towards products. Reactants have to cross this energy barrier. Now, because of this energy barrier, this is called as activation energy, EA. So this is the energy barrier reactants have to cross so that they reach products. This is average energy of reactants, this is average energy of products. If the same reaction is carried out in presence of catalyst, there is a possibility that it will cut down the energy gap and makes it possible for reactants to cross the energy barrier easily because the barrier has been reduced. So this is the new activation energy in presence of catalyst, EA dash. So this is uncatalyzed reaction. This is a profile diagram for catalyzed reaction. So you can realize that the catalyzed and uncatalyzed reactions, they differ in the activation energies. Activation energy of a catalyzed reaction is less than the activation energy of uncatalyzed reaction. Whereas if you see this energy difference is described as delta H. Delta H is called as heat of reaction. So I can put it here. Decreases activation energy and enhances the rate of reaction. Does not change delta H. heat of reaction in presence of catalyst and heat of reaction in the absence of catalyst is exactly same. Apart from this, another important feature of catalyst is it does not initiate reaction. Catalyst cannot initiate a reaction. It can only speed up a reaction which has already been initiated. So catalyst does not initiate reaction. These are few important characteristics of catalyst you should know. Lowers activation energy, does not affect delta H, heat of reaction. It does not initiate the reaction. It is not consumed in the reaction, and it is required in very small amounts during a chemical reaction. So these are important characteristics of catalyst. I want to make you familiar with another important term in this, that is AutoCatalysis. What is autocatalyst? Any substance which can act as a catalyst in a reaction in which it is formed is called as autocatalyst. For example, this is arsine, ASH3 is called as arsine. When it decomposes, it gives rise to arsenic and hydrogen. I can balance the equation. Right. This decomposition is catalyzed by arsenic. So, arsenic is able to catalyze the reaction in which it is being formed. It decomposes decomposition of arsine into arsenic and hydrogen. So, a substance which enhances the rate of reaction in which it is being formed is called as autocatalyst. See, one important indication of a reaction being autocatalyzed reaction is that it will be slow in the beginning. This reaction will be very slow in the beginning because in the beginning there is no arsenic. So, once a reasonable amount of arsenic is formed, this reaction picks up speed. So, if a reaction is slow in the beginning and picks up speed after some time, then you can expect it to be an autocatalyzed reaction. So, this is the autocatalyst in this reaction. Another example is, this is a very popular reaction. This type of substance is called as ester, ethyl acetate. If you react it with water, the reaction is called as hydrolysis. This is ester hydrolysis. Then you get acetic acid and ethyl alcohol. This substance produces H plus, which will catalyze this reaction. So, this acts as autocatalyst. The acid which is being formed in the ester hydrolysis will act as a catalyst for the hydrolysis reaction. I want to give you one more example, please. This is permanganate and this is oxalate. This acts as oxidizing agent. This is the substance which is getting oxidized, and when it gets oxidized, the substance which is formed is carbon dioxide, Mn2 plus water. MnO4 minus, you can see, has changed from +7 oxidation state to +2 oxidation state. Carbon has changed from +3 oxidation state to +4 oxidation state. So, this is another example of autocatalyzed reaction, and in this reaction the autocatalyst is Mn. Mn plus 2 acts as autocatalyst. Let us see how it helps in speeding up the reaction in which it is being formed. See, logically you can explain it like this. The oxidizing agent has negative charge, and the reducing agent, the species which is getting oxidized, has negative charge even. So, these two species cannot approach each other easily because they tend to repel each other. They tend to repel each other, so they cannot approach each other very easily. So, that is the reason why the reaction is slow in the beginning. Now, what happens after some time is when reasonable amount of Mn2 plus is formed, the left out MnO4 minus will then undergo a comproportionation reaction and produces MnO2. This is +7, this is +2, this is +4. So, it is a case of comproportionation reaction. Now, from here onwards, this oxidation of oxalate will be catalyzed by MnO2. It will be oxidized by MnO2. So a different type of reaction takes place. MnO2 plus C2O4 2 minus in presence of H plus gives CO2 plus Mn2 plus. Now you can see here these two species have identical, like charges, so they tend to repel each other. So approach of oxidizing and reducing agent towards each other will be a difficult task due to like charges, they repel each other. Whereas here this is not carrying any charge, so these two can approach very easily and can undergo a faster reaction, and this is formed as a result of this reaction. So you can say due to formation of this is due to this, and it is this species which is responsible for speeding up the overall reaction. So these are few examples of autocatalyzed reactions. Oxidation of oxalate by KMnO4 is an autocatalyzed reaction. Autocatalyst is Mn2 plus. Decomposition of arsine is autocatalyzed reaction, and the autocatalyst is arsenic. Ester hydrolysis is an autocatalyzed reaction, and the catalyst is the acid which is formed in the hydrolysis reaction. Now let's learn about types of catalysis. Types of catalysis. Here we have two types. A, homogeneous catalysis. And B, heterogeneous catalysis. Now, what is homogeneous catalysis? If the catalyst and all the reactants are in the same phase, then the type of catalysis is called as homogeneous catalysis. And if they are in different phases, then it is called as heterogeneous catalysis. For example, take the case of Haber's process for manufacture of ammonia. The two reactants N2 and H2 are gases, whereas the catalyst which is being used is Fe, which is a solid. So it's a clear case of heterogeneous catalysis. Homogeneous catalysis. See, here you can think of two possibilities. You can have all of them gaseous substances, or you can have them in solution phase. So gas phase or solution phase reactions are homogeneous catalyzed reactions, whereas in heterogeneous catalysis they are in different phases. Let us look at the examples of homogeneous catalysis. One example of homogeneous catalysis is hydrolysis of ester. CH3COO C2H5, this is ethyl acetate plus water, and then you get CH3COH plus ethyl alcohol. This is an example of homogeneous catalysis. And then another example, SO2 plus O2, this involves oxidation of sulfur dioxide to sulfur trioxide. You can balance it. Here we use oxides of nitrogen. This is a gas, and NO is also a gas. So it's a case of homogeneous catalysis because all the both the reactants and the catalyst are in the gaseous phase, in the same phase. Another example, this substance is sucrose. It's a carbohydrate, it's a disaccharide called as sucrose. Hydrolysis. In presence of acid, and you get C6H12O6 plus C6H12O6. While this is glucose, one of them is glucose and the other one is fructose. They are isomers. This reaction is called as inversion of cane sugar. This is cane sugar, sucrose. on inversion, because this is plus dextrorotatory, this is dextrorotatory, this is levorotatory. At the end you get a mixture of these two. This has more magnitude of rotation, that's the reason why the mixture will be levorotatory. So you are going from a dextro substance to a levo substance, that's the reason why the reaction is called as inversion. It's a case of inversion. All the substances are in solution phase. The acid catalyst, sucrose, and of course the solvent water are in the same phase. That's the reason why you call it as a case of homogeneous catalysis. I'll now give you examples of heterogeneous catalysis. Now let's look at some examples of heterogeneous catalysis. Heterogeneous catalysis, as I told you, reactants and catalysts are in different phases. Heterogeneous catalysis. Some examples, some important industrial examples for heterogeneous catalysis. One, you have this Haber's process. N2 plus 3H2 gives 2NH3. While nitrogen is a gas, hydrogen is a gas, Fe, the catalyst, is a solid. So it's a case of heterogeneous catalysis. Example 2, SO2 is a gas, reacts with O2 gas in presence of platinum solid. This is a catalyst, platinum, and you get SO3. So this is again a case of heterogeneous catalysis. As you can see, the reactants are in the gas phase, whereas the catalyst is a solid. Number 3 in the list is oil, that is vegetable oil, hydrogen gas. The catalyst used is a nickel, which is a solid. This is a gas, this is a liquid, and you get solid fat. This is hardening of oils for the preparation of vanaspati ghee, which is also called as margarine. So these are some important examples. I can quote one more example for you. This is Oswald process for manufacture of nitric acid. We oxidize ammonia gas in presence of platinum solid to get NO and H2O. So the oxidation of ammonia in presence of platinum catalyst is also a case of heterogeneous catalysis. So this is Haber's process, this is again contact process, this is hydrogenation of oils, and this is Oswald's process for the manufacture of nitric acid. Now let's learn about theories of catalysis. Theories of catalysis. These theories, they try to explain you how a catalyst works. So there are two theories. One is intermediate compound formation theory, and there is another theory, adsorption theory. Adsorption theory is, as the name itself indicates, it tries to explain you heterogeneous catalysis, especially catalysis by transition metals. First, we'll talk about intermediate compound formation theory. Intermediate compound formation theory. In this theory, we say that one of the reactants reacts with catalyst to form an intermediate compound. This compound is an activated complex. This will react with another reactant to give product, and the catalyst is regenerated. Look at the example. See, let's take the example of this. SO2 reacts with O2 in presence of NO and get SO3. According to this theory, the reaction first takes place between NO and O2. Please remember, NO is a catalyst here, and oxygen is one of the reactants, and you get NO2. NO2 is a intermediate compound. Now this NO2 then will combine with SO2 to give SO3 and NO is regenerated. This is the regenerated catalyst. Again this NO will react with fresh molecule of oxygen to give NO2. NO2 again combines with SO2 to give SO3. This is how the reaction is repeated several times. The same catalyst is regenerated several times and it will perform the same function of oxidizing SO2 to SO3. So this is one example where intermediate compound formation theory is being used to explain catalysis, oxidation of SO2 to SO3. Another example, one more example. This is again for this only, SO2 plus O2 gives rise to SO3. This time we'll see how vanadium pentoxide is able to catalyze this reaction. The reaction is explained in this way. V2O5 first reacts with SO2. It will transfer its oxygen to SO2 and SO2 will become SO3. V2O5 now will become V2O4. You can see in this reaction oxidation state of vanadium has changed from +5 to +4. Now V2O4 then will combine with oxygen and it will regenerate V2O5. This V2O5 is again ready to combine with fresh molecule of SO2 to give SO3. So here in this catalysis, in this reaction especially, there is an oscillation of vanadium from its +5 state to +4 again back to +5. So because of its ability to show variable oxidation state, vanadium pentoxide is capable of catalyzing this reaction. So we can say transition metals and their compounds are able to act as good industrial catalysts. When it comes to compounds, we say it is because of its ability to show variable oxidation state, it is capable of acting as catalyst. Whereas when it comes to metals, we say that they act as good adsorbents for reactants and therefore can catalyze heterogeneous catalysis, catalyzed reactions. I have given two examples to explain intermediate compound formation theory. Here the intermediate compound is NO2, whereas in this case the intermediate compound is V2O4. Another theory to explain catalysis is adsorption theory. According to this theory, the catalyst will provide surface for reactants to get adsorbed on it. See, the reactants diffuse from the gas phase onto the surface of catalyst, then they get adsorbed on the catalyst surface. The original bonds become loose and now new bonds can form. Because of loosening of original bonds, bond breaking becomes easy, activation energy comes down and therefore the reaction takes place at a rapid rate. So when the reactants get adsorbed on the surface of catalyst, they react there and transform into products. Products get dissolved from the surface of catalyst and they escape into the gas phase. They diffuse into the gas phase and fresh molecules of reactants come and occupy the surface. So this is how adsorption theory explains catalysis. I'll tell you once again. The first step is diffusion of reactants from gas phase onto the surface of catalyst. The second step is adsorption of reactants, which leads to loosening of bonds. The formation of product takes place on the surface, then desorption of products takes place, and then diffusion of products into the gas phase, so that fresh molecules of reactants again come and get adsorbed on the surface of catalyst. Adsorption theory explains catalysis of involving metals, transition metals. Transition metals, especially those atoms which are present on the surface, have residual valences and they can adsorb reactants nicely and can lead to product formation. Let's now talk about activity of catalyst. Activity of catalyst. See, this is your D block. This is 3B, 4B, 5B, 6B. This is 7th, 7B. Then this is 8th group. 1B, 2B. As per IUPAC convention, we can take it as 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. Now, this is D block of long form of periodic table. I hope you have realized There are three, this is a 3D series, this is 4D series, this consists of 5D series. You have scandium, titanium, vanadium, chromium up to zinc. This is cadmium, this is mercury. You might have realized this is scandium, yttrium, and this is lanthanum. Fine. Now, this is as per IUPAC convention. This is the labeling of the vertical columns of the periodic table. This is older convention, right? This is IUPAC convention. Now, what I want to show you is, for these metals to act as catalyst, as I told you just now, they have to adsorb the reactants. You know, adsorption is possible because of presence of vacant d orbitals in these metals. Now, if the number of vacant d orbitals are more, then they adsorb the reactants very strongly, and they will not leave the reactants easily. That's why such metals cannot act as good catalysts. Whereas, if the d orbitals are completely filled, then the metal will not show good tendency to adsorb substances on its surface, and it will not act as a good catalyst. For a metal to act as a good catalyst, it should belong to any of these groups from 5 to 11, or I can say from 5B to 1B. These metals act as good catalyst, and among them very good catalysts belong to these three columns, 7, 8 and 9. In the 7 you have Mn, technetium, rhenium, manganese, technetium, rhenium, and here you have iron, ruthenium, osmium. This is cobalt, rhodium, iridium. So these metals act as more efficient catalyst. They are not only good in adsorbing reactants, they are also good in dissolving the products, so that space is created for adsorption of fresh molecules of reactants. So catalysts of good activity are present in these vertical columns. You need to remember that. Third and fourth B group elements are not efficient because they are good at adsorption, they are not good at desorption. So there should be a balance between adsorption of reactants and desorption of products. If a catalyst is good in adsorbing reactants but not good in dissolving products, you cannot use it. Such catalysts belong to this. So you don't prefer using them as industrial catalyst. Now let's now talk about selectivity of catalysts. Selectivity. Selectivity, most of the catalysts are selective in their action. They catalyze a particular type of reaction. For example, if you combine carbon monoxide and hydrogen gas, if you do this reaction in presence of nickel catalyst, you end up with methane, and of course water molecules are formed. So this mixture of carbon monoxide and hydrogen in presence of nickel will give methane. Whereas same substances, carbon monoxide and hydrogen, if you change the catalyst, if you change it to copper, you get formaldehyde. And same mixture of carbon monoxide and hydrogen, if you change the catalyst to a mixture of copper in presence of zinc oxide and chromic oxide, Cr2O3, would give methyl alcohol. So you can see when you change the catalyst, the products are changing. That is what is called as selectivity. Catalysts are specific in their reactions. They give rise to one particular type of products. There's another type of catalyst which is called as shape selective catalyst. Shape selective catalyst. The example here is ZSM5. ZSM5 is an aluminosilicate. It is an aluminosilicate. It will have a formula of this type: KXAlX SiY O 2 into X plus Y, and some n number of water molecules of crystallization. This type of compound, it's an aluminosilicate. You can realize it's an aluminosilicate. Some of the silicon atoms are replaced by aluminium, x number of aluminium. So there used to be x plus y number of silicons. Now you have replaced some x number of silicons by aluminium. So you have 2 into x plus y number of oxygens. And of course, you have water molecules of crystallization. Formula is not that very important. What I want to emphasize here is this consists of water of crystallization. If you take a solid piece of this catalyst and heat it in vacuum, or low pressure, then what happens is it will lose its water of crystallization. When it loses water of crystallization, it becomes a porous mass. Several channels are formed here, so it becomes a porous mass. These are pores which are formed. It becomes microporous because of loss of water molecules from everywhere. The solid, compact solid now becomes a microporous substance. Now these pore size will not allow highly branched molecules into it. Now the pore size inside the pores, when a molecule goes, it is likely to undergo dehydration. So if you put alcohols, if you put this in alcohol, it will allow straight chain molecules to enter into it and get dehydrated and come out as hydrocarbons, whereas the branched molecules cannot enter and cannot get converted into alkenes. So this is a shape selective catalyst in that it will catalyze dehydration of straight chain alcohols. It will not catalyze dehydration of branched alcohols. Example, this substance is popularly or commercially called as ZSM5. It is a shape selective catalyst. It's basically an aluminosilicate which has been heated in vacuum to undergo dehydration. Once it undergoes dehydration, it becomes microporous substance and the pore size will not allow branched molecules.